Well, I didn't even invite him. He wasn't on the invite.
Yeah, it's because he didn't, I think he needed to drop the course to get into his another class, and then he never signed back up.
Probably our gain. Okay. So I'm going to bring up a couple of things here. Do I have it up on here? This is the one we're going to use.
Is the course on Blackboard yet?
It's sort of. I copied over my 200 course over on top of this course this morning by accident, so I'll get it fixed when I get back, maybe right after class. Because it either has to be right after class or when I get back from dinner tonight. But between the two, it'll be fixed and opened up and all that jazz. Okay. Oh, this is homemade?
Yeah. You thought I bought it?
That's what I would have expected.
No, I made it 3 hours yesterday.
You had time to do that after you made fish?
What do you want with fish?
Oh man, there's just so many layers of inside jokes in this room. Okay, so we're going to do a couple different things in here. So for starters, we are going to, whoa, hello. Ninja, oh, there, got it. All right, actually it might still come through because I think it's coming through the HDMI. That probably turned it off. So, oh, that's how you do it. All right, so this class officially is called Systems Programming. What does that mean? What does that mean to you? Go ahead.
Programming having to do with the operating system.
Okay. Yeah, that's a good one. Okay, what does it mean to program operating systems?
Program a system that will allow non-tech savvy people to interact with the system.
Okay, so one thing is programming the operating system itself, creating a software product that sits between the end user and the hardware. All right, so that's one thing. Make the, actually let's call it low level OS. Okay, so let's just burn past that for a second. We're going to talk more about that today. What else goes into an OS? What are some examples of OSs? Give me that first. Okay.
Android.
Okay.
CPM.
Windows. Okay, so far everything, well, Linux technically is an OS. Windows is a distribution. Ubuntu or Fedora or Slackware or Debian or Raspbian, these are all distributions of Linux. What's the difference between an operating system itself and a distribution? Well, like, so when if we're talking about Windows 10, what's the actual operating system for Windows 10?
Windows NT.
Yeah, it's the NT kernel. NT kernel is the actual operating system for Windows NT. For Linux, it's the Linux kernel. For prior to Windows XP, on the Windows side, it was the 9X kernel. Prior to that, it was DOS. DOS was the actual operating system. DOS was a little bit weird because it was the operating system, but it was also the name of the distribution. So what's the difference between an OS and a distribution?
With the example of Linux, you could have multiple distributions of the same operating system.
Okay, so what's the difference? What makes something more than an operating system instead it makes it a distribution?
The UI is different.
Okay, well,
That's one visual difference.
well, you probably have a UI,
Okay.
right?
Sure.
So the OS itself doesn't necessarily dictate a fancy schmancy graphical user interface. You know, it probably implies some sort of baseline minimalistic user interface, UI, right? What else?
Would the distribution just sort of be how the user interacts with the operating system?
Okay, yeah, so let me try to rephrase. Let's throw you in there and then I'll.
Is it just like the bundles of like non-essential applications that come with it?
Well, let's flip that. Probably the bundle of reasonably essential applications. So like, you know, basically you guys both said the same thing is, you know, the OS plus the essential applications that are assumed to be there post-install. So in our world, this is likely what, like a text editor, web browser, we'll just do it, etc. Some sort of a file directory browser thingy, right? You know, so things that you are used to using for your daily life in an operating system. Things that wouldn't be essential is like Android Studio likely would not come pre-installed in a distribution. Interestingly enough, many Linux distributions come with a whole bunch of programming tools built into them because a lot of times Linux distributions, programmers tend to use Linux as maybe their go-to cool kid distribution, something like that. Do you have your hand up?
Yeah, then for the OS, could we call that a bundle of system calls?
Okay, so let's call OS, why don't we, bundle is fine but weird. Let's call this collection of system API calls or API functions that interact with the user system. So that's the layer that's sitting between the user and the operating system, and the hardware. As well as provide the essential functions of an OS. What are the essential functions of an OS? Most of you, hopefully all of you, have had 350. So 350 would be the theory side of this class, right? This is more the applied side. Go ahead. So what are some essential functions of an operating system?
Like memory management,
Okay.
scheduling.
CPU / process. Actually, I kind of liked what you just said. You just said scheduling. Various forms of scheduling. Anything else?
Like file system stuff.
Yep, file system. I/O. Most modern operating systems have a driver subsystem. When we say driver, what does that mean? If you create a driver for, you get your brand new graphics card and you install the driver for that, what is that? Go ahead.
Isn't that just like the software that tells the hardware what to do?
Okay. Now, when you unpackage your new $1,000 graphics card and you put it in your machine, does that mean it won't work until you install the software, or does it work at some basic level?
I think it would work at some basic level.
How many of you have ever installed a super expensive graphics card? And what happens right after you install it? What's the first thing you see? Really low resolution, 640 by 480. Hello, I am a $1,000 VGA generic graphics card.
I'm not working.
This is what I'm able to do without my driver installed. Okay, so built into the operating system is a baseline driver that says, look, all modern graphics cards are VGA compatible graphics cards. VGA is from a long, long, long time ago. It's a standard that says this graphics card will not be able to do all the bells and whistles and all the extra special OpenGL and DirectX and take advantage of its 12 gigs of RAM and blah, 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 extra cores. It can't do any of that stuff, but it can show a picture on the screen. because it's using the default VGA driver that comes with the operating system. Before we had driver subsystems, you had to have the operating system itself have drivers built into it. We still experience that on Mac OS. So for instance, if you have a Mac OS, you've heard me give this kind of spiel before about Apple hardware Apple's stuff tends to just work because they're writing software for their own hardware, right? So when you get the latest, greatest MacBook or the latest, greatest iMac, whatever it is, whatever graphics card comes in there has this custom built driver just for that. And if you get one of the new, and this has historically been the problem with the Mac Pros, which is their expandable tower thing, is you are at the mercy of what graphics cards they choose to support. So you get this tower that, yeah, you could open it up and you can slam a different PCI Express GPU in there, but unless there's Apple support for it, it's not going to work. Even if you switch over and do boot camp and run Windows, there's oftentimes problems. You have to get the Macintosh version of a card. It's not that friendly. So Apple puts their own extra little defenses in there between the hardware and the, the expandable hardware and the normal computing hardware. All right, but with a driver subsystem, for instance, Windows, Linux, these all have driver subsystems. This allows you to have a core operating system that supports kind of your generalistic common hardware, floppy disks, CD-ROMs, even though these things aren't even things anymore. But you get what I'm saying. Hardware that has a default level of operation that's been around for a long time that you assume will always work. You plug a USB stick in, it should come up as a little shared drive, something like that. But then it has a subsystem that allows third-party vendors to write software that tells the operating system how to make hardware that was not invented the day that operating system was compiled work with that operating system in terms of that operating system calls. You know, here's all the cool stuff the operating system knows how to do, and all that stuff is going to have to do with I/O and us seeing stuff or us getting output or, you know, whatever, number crunching stuff behind the scenes. These are the basics of what computing is. So those things are all captured through this big collection of system calls in our operating system, which we could also think of as the OS's API. But the software driver allows us to convert signals coming in from, for instance, the graphics card into what should actually happen when said GPU ramps up and needs to start pushing frames per second and that kind of stuff. All right, so a driver subsystem would be something else that's in our modern operating system. So we'll just throw a little et cetera there at the end of that. All right, so the operating system itself, and really if we think about a historical operating system, we wouldn't really have necessarily this system call API. Instead, you would just have a hard-coded OS that knew how to talk to generic everything, and whatever was built into the OS, that's what the OS came with. And if you needed a update, you would have to buy the new OS. There was no over-the-air software updates or security patches or anything like that. So our modern-day operating systems are often built on top of what's called a microkernel. With layers of system API, which can be easily updated / expanded. All right, so there's going to be some level, some core OS level, this microkernel, that's going to say, this is the operating system, dude's likely not changing until the next time you install a new operating system. But then outside of that, you have layers of things that might actually change. Yeah.
So I'm clear on some of the terminology we're using. Would DOS and CPM, would those be distributions or OSs?
I mentioned like with DOS, it's kind of both. Okay. So DOS is the actual operating system, but it's also a distribution. It comes with edit. It comes with So let's just say yes. At the end of the day, it doesn't really matter. We tend to use the names interchangeably, right? So it doesn't matter if somebody says, what's your favorite OS, and you say Windows. Everybody knows what you're talking about. Just officially, Windows is more than just the operating system. It's the expectation of all the stuff that comes prepackaged with it. Okay? All right, so systems programming, we might want to write an operating system. We're going to talk about what that means. What else might systems programming be?
Maintain an operating system.
Okay, so maybe write tools that interact directly with an OS, likely in terms of its system calls. Something like that. So OS already exists. Now you might want to write something that empowers the OS to do something else. Ultimately, if it was systems programming, you're probably writing something that's part of the layer that interacts with the actual operating system. So writing an app that runs on iPhone or runs on Android, more times than not, is not going to be a systems application. It's a user application that is built on top of the user level API for Android or iOS, or even if you're writing Mac OS or Windows applications. Only when you start interfacing directly with the system calls could you start calling that a systems application. You start creating threads. I think you did that last semester, right? You created threads, you created processes, things like that. You start dealing with inter-process communication, semaphores, signals, shared memory. These are all things that are built into an operating system in terms of its kind of core abilities to have, if you think of an operating system like a city, and the processes that are running on the operating system as like people that live in that city, and we try to think about our real life as, hey, I want to call my buddy down on the street. What are the different ways I can communicate with them? Well, you can text them. You can email them. You can make a phone call. You can go old school and leave an envelope with a note in it under some shrub that maybe you guys both know is there. Okay, they call it what, a drop point? Isn't that what they?
Dead drop.
Who?
Dead drop.
Dead drop. You know that pretty well. What's the?
Breaking Bad.
Oh, I saw that whole show, but you've probably seen it more recently, maybe. How many of you have Hulu? Okay, homework assignment. Watch the movie The Art of Self-Defense. It's like amazing. It's pure Lippman humor too. It's great. Every night, I watched it once, and now every single night I sit there and I fast forward and watch. I have like a 20-minute version of the movie where I watch all the good parts for like 9-10 nights in a row now.
Do timestamps written down?
No, I just flip through it until I see the scene. It's super good, but definitely worth The Art of Self-Defense. Totally worth seeing, and has like legit actors in it. Okay, so some point it doesn't matter what we call an application a systems application or not, and there's probably some sort of gray area where, well, I have an application that's really doing a lot of user level stuff, but it's also spawning off threads and doing some other things. So is that a systems application or is it a user application? It doesn't matter. Okay, typically I think your rule of thumb would be if it's making at least one system call to your operating system's API, probably a systems program counts. Whatever. Okay, but all these guys are related because of this slide right here where we talk about a modern operating system is a microkernel which has various layers that surround it until we get up to the user level. So there's all sorts of stuff that is kind of a hybrid between user application stuff and system stuff that sits above like ones and zeros. Make sense? And anything in there is interesting. Okay, so in here we're really interested in those interesting type of applications, things that are happening under the hood. Okay, we're not looking at the the beautiful front end application or something like that. We're thinking about how do our actual computers work at the software level. All right. Our 325 course talks about how do our computers actually work at the hardware level. You know, how does your CPU put together with registers and things like that, and how does the memory physically hook into the ALU, physically hook into the CPU, and what's the role of the motherboard and all these things. These are all hardware issues. In here, that exists. We have this thing called the motherboard that makes all those things talk. Great. Okay, now we're saying, I want to write software that leverages those things. Those are the resources of our computer. Our computer has RAM. Our computer has a processor. Our computer has a hard drive. Okay? We have the various components of our computer, and I think of these things as a pile of resources. And from a modern computing perspective, we might say, what are the things that I should be able to do to fully take advantage of those resources? It doesn't matter if you have, let's talk about resources. Who has a lot of memory on their computer in here? Or if it's not in their laptop, it's their desktop. Who has at least 16 gigs of RAM in their machine? 32. 64? These are pathetic.
A broke college student, what do you expect?
I have 4 gigs in my shoe. Well, no, I mean, because I was in Aruba in December, and I stepped on this weird, like, super hot rock, and I took a chunk out of it, so I took a 4 gig chip, snapped it in half, and I glued it underneath, so I have 4 gigs in my shoe.
Well, if you snapped in half, one would be good.
Well, I don't know you don't know which half I took off. A lot of that might have been the silicon, not the... All right, so we had a couple people who have 32 gigs of RAM, right? Okay, why 32? What are you doing with 32 gigs of RAM? What do you think, Francisco? You got 32 gigs. You're the only one with 32, right? Somebody else had 32? Oh, just 16.
Different, either like simulations or music.
Simulations or music. Okay, tell me, let's pretend that you didn't say the simulation thing because I think it's made up. So let's assume that you're talking about music. How is that music taking advantage of your 32 gigs of RAM?
I would assume it's all the different software instruments that I'm like putting on each track.
How does your computer use RAM? Let's talk about that. What's the purpose of RAM? So we just said a minute ago that, you know, when we think about our computers, we have this pile of resources. And all these resources serve different purposes, right? I mean, they have to, otherwise we wouldn't have a difference between RAM and hard drive. And, you know, we have these different resources, and the motherboard puts all these things together because we need some way for them to talk to each other, because that seems to make some sense. So one of those things is our RAM. What's the job of RAM? What's its purpose? Go ahead.
Remember things, but get them to me quickly.
Okay, so relatively fast,
Yeah.
store crap, and relatively short-term storage, right? So most of when we think about RAM, it requires electricity. So our computer, whatever's in memory, you're in your RAM, is only in there as long as you still have power. As soon as battery goes out, or you unplug the thing, that thing drains out. So it's almost like, like a fire hose, like pushing electricity there, and it's holding it in this state. And we talk about that in 325, like how memory's built. How do you actually design memory? But effectively, it's holding it in this state. And if any of this energy that's doing that fails, all gone. Whatever 0 or 1 you were storing in that state, gone. Okay? Why am I on a different... I don't have access to Res Hall in here?
Shit, it runs off the same network. It's a little
Whatever. There we go. Okay, so that's so that's the role of RAM. So what are some things we might use memory for in our computer? When you double click on Microsoft Word, how does that use RAM? So this is more of a 350 topic, right? Go ahead.
Well, the OS communicates to your file system to send it to your RAM.
Okay.
Your memory.
One way or another, right? modern operating systems, they're gonna go and locate Microsoft Word on the file system, and they're actually only going to load part of it into memory. And they're going to usually, most of our modern operating systems use some kind of paging memory management. So they're going to create a whole bunch of frames, and a frame is the same size as a page. They're going to split Word into a whole bunch of little pages and stick them in frames and throw the frames into memory. That's what happens, right? And what's nice about paging is those things don't need to be sitting right next to each other in memory, kind of like a linked list, right? So you can make some connections to other data structures and things like that we've talked about. All right, so one way or another, parts or the important parts of Microsoft Word have now gotten into memory. And we have those in memory because you're running that application in real time, right? And you need to access that relatively quickly. Now, when you actually perform actions within Microsoft Word, when you click on something, some assembly instructions occur, right? Somebody wrote some C program or something like that, but behind the scenes, that compiled down to a low-level language, assembly, that has a one-to-one relationship with the CPU, and now your CPU is going to start firing, and it's going to be moving things between system RAM and super fast memory that's on the CPU, called hardware registers or one of the caches, L1, L2, L3 cache. You know, closer you get to the CPU, the smaller and the faster and the more expensive per bit memory gets. That's your punchline. Farther away you get, bigger the memory, cheaper the memory, slower the memory per bit. But we want a big hard drive to hold lots of Francisco's music that he mistakenly thought, hey, I need a lot of RAM for that. But really, he just needs a 2 terabyte hard drive. It doesn't even need to be a solid state hard drive if he's just holding music. Right? Solid state hard drives are for that move when you've double clicked on Microsoft Word and you want it to get from hard drive into memory fast, right? Because your seek time on a solid state drive and then your load time on a solid state drive is significantly faster. It is significantly faster than it would be on a solid or a mechanical hard drive where there's spinning disks and things like that. Okay, so that's why solid state drives are faster. But ultimately, a solid state drive versus an HDD, standard hard drive, these guys are performing the same task. You could just move stuff faster between the hard drive and RAM with a solid state drive. You can look up stuff faster on a solid state drive than you can on a hard drive. All right, but that's that. But the trade-off usually is if you have $200 to spend, you can get a bigger traditional hard drive than you can solid state drive. We're starting to get to the point where that's not as true as it used to be, but at this point, you can, what's the biggest single hard drive you can get? What, 6 or 8 gigs? Or 6 or 8 terabytes rather?
That's a lot more than that nowadays.
For a single disk?
Single disc, yeah.
They made one that was 16, an SSD, 16.
Oh, I was talking about traditional drives, but
Oh.
yeah, a 16 terabyte SSD drive I'm sure exists, but
You're pushing it.
you're taking out a house mortgage.
What do you like, 8 or 10?
Yeah, 8 or 10 gigabytes, and so terabytes. Sorry, let's just go exabytes, and we'll just stay ahead of the curve. So, in any case, each of these pieces of hardware or computer has a role that it plays, right? And the role that memory plays is it is a staging area for software applications as their code needs to potentially get run onto the CPU. That's the role it plays. And anything that we are directly interacting with on our computer at any point in time is stored in system memory, and that in Francisco's 32 gigs. So is it impossible that he wouldn't need 32 gigs for his music? Well, it's not impossible, but you're actively listening to a lot of music at once. Like a lot of music at once. Well, which is fine. So even with that in mind, so now you have, so he was referencing multiple tools, right? So you have 5 or 6 different software applications, things like that, and each one of those is going to start taking up system resources. Again, that's probably not going to be using up 32, but you might struggle with only 8. Maybe 16 is the more appropriate. So this isn't a common, this isn't a problem that an individual runs into. Like, you know, we're not just beating up on Francisco. This is a problem that modern computer scientists run into. Because as human beings, we like bigger, faster, better, whatever. You know, that's our thing. We want faster internet. You know, what speed internet do we have at our house? You know, now some places are selling Gigabit Internet. Right? The reality is you had Gigabit Internet at your house. Very, very, very few sources are going to be able to serve you data at gigabit speeds. So what do you need Gigabit Internet for? What value are you getting? Just bragging rights? Francisco has the bragging rights. I got 32 gigs of RAM. Ha! Ha! Okay. I have Gigabit Internet. Ha! So how does that get used?
Doesn't faster speed also mean you have slightly more bandwidth to play with, so you can do more things at once?
Yeah, that's the thing. That's the thing. It's a matter of being able to do multiple things at once. You can be downloading your music with some of your bandwidth. You can be streaming a Netflix show on another one. You can be doing 5 or 6 other things, and you still have bandwidth left over to have active searching and things like that working at your house. Okay, so you have a big enough pipe of data flowing into your house, enough bandwidth to spread across all the different applications you might use internet for. Make sense? Okay, same thing's true here with our 32 gigs of RAM. Now, every now and then, you know, you were mentioning he does software or music creation stuff. He might be doing something really crazy. It's using a lot of tools, maybe something that's doing some encoding, that's probably using more memory than your average, probably still not pushing your 32, but that's the time when you want to have that bandwidth. Same thing we were talking about earlier with our $1,000 graphics card. 95% of the time, you're not maxing that $1,000 graphics card. But you got that $1,000 graphics card for that 5% of the time, when everybody else is having frame drops and you're still sustaining 83 frames a second. So, you know, that's the purpose. So we have overpowered resources that, as modern technology folks look at these, we have trouble using a resource by itself to its maximum. So we look at other things that we can do. So with 32 gigs of RAM, this machine has 64 gigs of RAM in it. Can I use 64 gigs of RAM in a laptop in any sort of reasonable thing? No. So that's where we come into virtualizing machines. So I have Mac on here, I have Windows on here, I have 2 different versions of Linux on here that I can just launch at any point in time that I want. And it's running as one of, so if I want to, we're going to mess with Ubuntu in here, for example. So now Linux is running. So I have a Linux operating system running here. I think I've given it 8 gigs of RAM or something like that, and maybe 4 processors. And this thing has dual 6-core i9s. So I have lots of system resources that I could split across multiple virtual machines. This is the value of having a lot of those resources. And one of the things, so what we're seeing here is kind of the idea of modern operating system design. We're moving towards virtualizing operating systems using a single group of hardware and virtualizing operating systems, multiple operating systems across that single group of hardware. So in the department, we just got 3 new machines that we're going to hook together. We have 4 8 terabyte NAS drives, and the 3 machines are all dual processors, 6-core Xeon processors. Each machine has 128 gigs of RAM in it. And we're going to use it to serve virtual labs. So you want to spin up 60 Linux boxes all at once? You use VMware and you spin up 60 Linux boxes at once. And now you have 60 people all remoted into this computer cluster, all using the one group of hardware that each has, so this machine has hardware, this machine has hardware, this machine has hardware. They're all running software. And that software allows these guys to all talk to each other and now share that hardware across multiple virtual machines. Now we're getting use out of the hardware. So the operating system's meant to distribute computing power across software use. Yeah.
I was curious, do you think that's why Apple's new Mac
Well, it depends how you end up using it. Most people wouldn't, probably not for virtualization unless Apple gets into that area. That doesn't seem to be an area Apple really plays in a whole lot. And because, like for instance, one of the biggest weaknesses of virtual machines is you can't virtualize macOS officially. You can't legally virtualize the macOS. There may be some things you could do to virtualize the macOS, but you know, anybody who's going to do that at any sort of enterprise level, you can't screw around with, you know, illegally distributing stuff, right?
Well, in
You
the
know,
same way you can't legally run a Hackintosh, right?
you'd be, I believe that's true. You'd be in violation of Apple's terms of use for their.
But it's the same sort of stipulation.
Yeah, I wonder how that actually works though, since Apple's operating systems are free now. But I'm sure they have some very high-priced lawyers that have written the right stuff in there that would give them the right to sue you if they were interested in doing so. They probably wouldn't be. They would probably be more interested in the fact that you're running their software, probably not getting the best end-user experience, and will eventually just go buy an iMac. so it's the Hackintosh is the gateway drug for Windows users to ultimately purchase a Mac. Is that somebody's story in here? Oh, we're getting close. Who's huh?
I want to build one.
You want to build? Oh, that's a yeah. I mean, it's interesting, but you're gonna have driver problems. Yeah, there's some hardware lists out there you can look at that say this is the most compatible. And Blade years ago had a Hackintosh running on a laptop, ran shockingly well. Yeah, must have just been a moons aligned situation.
No, but gateway drug I did have is the Pi got me onto Linux.
Yep, and that's what we're trying to do in the department now. So almost all of our classes are going to be running on top of Linux now. So we're handing out quad-core Pis in 175, and they're going to use it throughout the 4 years, and then we're using Linux. I'm using Linux in 200, in 300. Most classes now are going to use Linux. But in any case, so this is an operating system running inside of a virtual machine, which is sharing some of this computer's hardware. So this computer's hardware right now is split across, well, right this second, it's split across the Mac OS and I click on Ubuntu and Ubuntu. So I have two OSs running right now. One is running natively on the hardware. The other one is running within a virtual machine that is running natively on the hardware. Make sense? So virtual machines are kind of our way of abstracting our computer's hardware across multiple operating systems that might be able to take advantage of additional system resources that we might not as individuals utilize. Yeah.
So you mentioned that the virtual machine was running directly on the hardware. It's not a process running within Mac OS.
Well, it is. Yeah. So the virtual machine itself is a user application. Right. That most of them anymore, like I'm running Parallels, which uses something, Apple has an API called Metal that allows pretty large portions of that to run directly on the hardware for performance. But you're right, it is Parallels is my virtual machine. It is a user application running on top of Mac OS, which is running on the hardware, and now I have Ubuntu running within that virtual machine.
Okay. Just trying to understand.
There's what is I think is a class. Was it a class 1 hypervisor? I think is what it's called. I might be getting that screwed up, but let's just pretend like it's accurate. But yeah, so we have our system resources in our computers, and often we don't use those to their fullest. Yet we need an operating system to help us manage those things, or a collection of operating systems that will help us manage those things. Make some sense? So here I'll put Ubuntu to sleep. So now that OS is asleep. Okay, so when we think about systems programming, they're going to be things related to systems. Okay? Having said that, I want to think about the low level first. Writing an OS. how do you write an OS? So if I sit there and I say, okay, we're going to write a, oh, and by the way, a couple people have some time conflicts, so you're going to see folks popping up and leaving and coming back or whatever, so they can watch the videos. If I say write an Android app that does something, we pretty much know what to do. If I say write a C# application that does something, we pretty much know what to do. So anytime we're starting with something that is a user level application, especially now most of us are juniors and seniors, we pretty much, user level applications are in our wheelhouse. That makes some sense to us, right? Figured, wow, I've done a bunch of those. But now what if I said, you know what, here is a pile of hardware. A Raspberry Pi with nothing installed on it, or a Dell computer with no OS. Okay, this basically has a motherboard, some hard drives, RAM, whatever, all the stuff you need, but no software. And I tell you to put an operating system on there. Well, what do? You go find somebody else's operating system first, right? You got a key for Windows, you install Windows. You got a, want a free OS, you go and get Linux, put Linux on there. All right, but what if I said, no, you got to write your own operating system to write on this? How does that work? What does it mean to write your own operating system? How does that even begin? It's magic.
Would you have to write it somewhere else first and then take an image of it and put it on there? Like you would have to, like.
Yeah, fair enough. Fair enough. So you're gonna write your OS on some other system that's already up and running now, which does become interesting about who wrote the first OS, right? Well, at some point we'll talk about that once we get a little deeper, but that might be a little abstract for us right this second. Yeah, so you're probably going to use another machine as your development machine, but your ultimate goal is I'm going to put an OS on that computer that I made, because all these OSs that have been around for all these years and they're secure and they're useful. Who wants that? When I could write my own buggy OS that doesn't do anything. That's where the real money is. All right. So if that was the problem you were being asked to do, what's the process? What's the high-level process for writing your own operating system? What do we know about computers? We have to step back. So what have we talked about so far today? We really talked about what a computer is, right? Thinking about it in terms of the collection of hardware it is. So I'm going to actually bring up a site. So one of the sites we're going to use pretty heavily, and you can kind of look ahead on this, but we're going to use some of their examples in here, and even we're going to mostly actually follow what they have in here. It's called littleosbook.github.io. There's a link for it on Blackboard once I fix the class. So it's there. You won't have to memorize it. But in any case, they're going to take us through this, but we're going to deviate from it with our own features and stuff like that. So don't necessarily view this as our only option. But using, and we're going to go through some of these things. In fact, we can even mimic some of the stuff here in a few minutes. But I want to start at this top level here. When we think about a computer, before I scroll down anymore, our modern computers have something called a BIOS on them. What is a BIOS? What is that guy? What's its purpose? Go ahead.
It sort of helps you load the other applications as the OS is booting up, in a way.
Okay.
Like packages come with it. Yeah, that's not
Go ahead.
enough.
It takes inventory of what hardware there is.
Okay. So kind of putting the two things together, maybe it's kind of the OS before the OS. It's an extremely simple OS that kind of collects the resources that you're working with. This is how much memory I have. This is the hard drives. These are all, and this is maybe how I can talk to these things. Okay, so it's a basic input-output system is what BIOS is. All right, so you're figuring out what do I have to work with. You're kind of cataloging your toys, and then you're saying, okay, now what? Okay, so that we go through that BIOS to make that next step. Now, if you were inventing computers way back when, now the early computers had everything hard-coded. Like actually the wires were hard-coded. This computer does what this wire says for it to do. right? And as soon as we started thinking, you know what, I really want this to be software controlled. I want my computer to be programmable. All right, now we're starting to think, how do I write software that will integrate with this hardware? How would you do that? What's the process?
Well, first, you have to know what the hardware can do.
Okay, well, you already know that. You know that you have memory holds stuff, and they hold stuff at different speeds and things like that. But ultimately, if we go from, I have this pile of hardware sitting here, and I want to get to a prompt that will let me type the letter A in there or something like that. Very simple operating system. Maybe it's not even a prompt. Maybe it just is an operating system that says, hello world. That's what the OS does. It boots up and displays hello world on the screen. All right, so if that's what the OS you're trying to do is, what's the process? And I'm not asking you how it works. I'm asking you how you would make it work if you were inventing that process. It's a different question. Where is your OS going to live? Probably on the hard drive?
Yeah.
Okay. OS is going to live on the hard drive. Now, ultimately, where's the OS going to get loaded into once the machine powers on? Under the RAM. Okay. Now, who actually makes the OS move? The CPU? It's going to start working through instructions that say do this, do this, do this, do this, do this. Right? Okay. How does the CPU, where does the CPU start? We think of our CPU kind of like Pac-Man. CPU eats, right? And you need something to kind of get the ball rolling. And the CPU starts looking for a place to eat, place in memory to start eating. Do we have to have kind of a known starting point? Okay, so we're probably going to pick some spot in memory that we need to make sure we put our, instruction number 1 in that spot, right? Because that's where the CPU is going to immediately run and start eating, and that's going to take it on its voyage someplace else. So at some point, we have to have that starting point that we've dictated this is where it begins. That make sense? All right. So now we do have, there's some things that exist. So BIOS is a programmable piece of hardware. We have something else often called a bootloader. Anybody have we heard of bootloaders before? Okay, what is a bootloader? Do you know what that guy does? What its purpose is? Go ahead.
If you had, what was in the latitude years when you switch between Mac and Windows?
Okay, so is it fair to say that somehow that guy knows how to kind of, if we put the bootloader in that first step where the CPU starts eating, and the bootloader comes up on the screen in whatever format, whether it's a nice looking format or it's a really crappy, looking UI, whatever it is it fair to say that maybe a bootloader knows how to take the second step? It allows you to maybe conveniently get your OS into some sort of a standard place in memory or something like that. So some people maybe have invented bootloaders that operate. How many of you have heard of the MBR in a hard drive? Master boot record. You heard of that before? The master boot record? Bootloaders typically get put into the master boot record of your hard drive, because that's the first place that the hardware looks to load whatever it is you're saying your OS is. Modernly is typically a bootloader. We'll take that and load it into the right place in memory for the CPU to start eating. All right, so modern bootloaders, like for Linux, the bootloader is called grub. All right, so grub is a piece of software that's already been written one time, but it's generically written to load operating systems. It makes sense? Okay, so with grub, if you install 6 different versions of Linux on your computer, you can have a single grub bootloader. Well, you would have a single grub bootloader that would have, when you first boot it up, it would give you 6 options for which OS you wanted to go to. Make sense? Boot camp is a bootloader on the Mac. So when you turn a Mac on and you hold the Option key, it pops up to something that usually shows you a couple hard drives. It says go to Windows, go to the Mac. You know, you choose which one of those, and it launches the OS off of the master boot record of potentially that partition. So if it's a different, if it's multiple partitions on the same hard drive, you might have one hard drive split in half, Windows on one half, Mac on the other half, something like that. Or you might have different hard drives, but that bootloader is the thing that says where to go next. Make some sense? All right. So it might make some sense for us as OS writers to leverage the fact that there's already bootloaders out there that say, hey, look, as long as you make the correct opening move, okay, you do the correct opening move, we can handle it from there to get your operating system running on modern hardware. Otherwise, you can invent your own bootloader that just plays by the rules of the hardware. Make sure you put it in the correct starting place in memory, and so the CPU finds it first, and then that instruction goes to some other instruction. So we're using something like Grub, which is what this book does, takes advantage of that idea that somebody's already solved the problem of taking our low-level system software and getting it to step 3. Step 1 to step 2 is the BIOS. Step 3 is now it's running on the CPU. Who gets us to step 3? The bootloader. So if I scroll down a little bit here, I think there's pictures. Here, I'll actually walk through some of these things as we get here. So, in fact, let me pause for a second. Any of you on your computers, oh, go ahead.
I was just, you mentioned step 1, step 2, step 3.
Mhm.
Is it a complete handoff, or like from BIOS to bootloader, or is it like I'm still running, like I'm still doing this, but like here's your trend?
Well, it just stages things in different places. It's not so much the BIOS. So the answer would be yes. It's a complete handoff because the BIOS has finished its task, right? Once the BIOS is up, it's done its task and it's said, okay, I've done this and I've put it there. The BIOS no longer has anything to do. You know, it's so whether it's handing it off or whatever, I've completed my purpose in life type thing. In here, I'm going to do all of our samples using Ubuntu Linux. If you want to use a Raspberry Pi or any other form of Linux, I'll give you a link to something else as well, but we're going to use something called unless you have your own virtual machine. If you already have a license to Parallels or VMware, so VMware on PC, Parallels on Mac. There's also a product called VMware Fusion on Mac, but Oracle makes something called VirtualBox, which is free. Okay, so I would recommend you download VirtualBox for your machine. And VirtualBox is a software application that will run on your computer, whether it's Mac, whether it's Linux, whether it's Windows. You get VirtualBox. Then, once you have VirtualBox, and I have a video that I can put up that'll show you how to install this. This is what I want to get done. Everybody should have this up and running by Monday next week, and we can talk about it on Slack, but this should be fairly self-explanatory. If you're going to use the same thing that I'm going to be using in class, we're going to use Ubuntu 18.04. So if you go to download, you want to go to Ubuntu Desktop. It actually doesn't matter if you do any of these other ones, but do Ubuntu Desktop. I would do 18.04. It's what they would call their latest stable version. 19 is their latest version, which is fine. It's fine. But I'll do all my examples with 18.04. It's the one that if you were running Ubuntu in an enterprise environment, it's the one they will support. Okay? So ultimately, once you install Ubuntu, and I'm actually going to go back, I'll walk us through this process here today.
So 1.9 megabyte download.
Yeah, it's an operating system.
All right.
Yeah. So it's just like Windows or Mac OS. So say a couple gigs, download it. VirtualBox will, say I want to create a new virtual machine. It'll ask you to choose how many resources you want to dedicate to your virtual machine. Now, one thing you do want to consider when you're doing this, now, what's nice about Linux, say running Linux in a VM. What's nice about Linux is you can run Linux with fewer system resources than it would take to run like Windows. So for instance, we take somebody like Jack who only has 4 gigs of RAM in his laptop. He can run Linux. It might be a little sluggish, but realistically, he's probably going to want to say, I'm going to do a minimalistic install, and I'm going to give it 1 gig of RAM. Something like that. You can probably run Linux in 1 gig of RAM. You might actually want to look at Raspbian. There's so Raspbian is the version of Linux for Windows. For the Raspberry Pi, and it uses relatively low system resources. Or I can get you one of the quad-core Raspberry Pis. It won't be as convenient, but you can at least run it on a monitor and keyboard or something like that. There is a way to actually run it and remote into it from your laptop and just use that as system resources. It's a little bit janky, but there's a way to do it to run that as your, quote, virtual machine on real hardware. But we can burn that bridge. But generally speaking, I would say if you're going to run Linux in a virtual machine, or you can dual boot. You can run Linux natively on your laptop and just dual boot into it, give it all your system resources.
Yeah, I mean, I've got a ThinkPad, so I'm thinking I could maybe just wipe that and put a Ubuntu onto it.
Yeah. Okay, so when we run Linux, I would say you probably want 2 gigs RAM. You don't need tons of hard drive space, so you can just give it like 10 gigabytes of hard drive space, 20 gigabytes of hard drive space. We're not doing anything crazy. And maybe 1 CPU. If you have a lot of system resources, you can give it more than this, and then it'll be a more robust machine. But remember, anything you're giving to your virtual machine, you're taking away from your host operating system. All right. So if Jack here has a dual core CPU, so he has 2 CPUs, he has 4 gigs of RAM, and he has whatever hard drive size is, but let's just operate off those first 2 things. He's giving half his CPU power and half his RAM to a virtual machine, which means that his Mac is now running on 1 CPU and 2 gigs of RAM. Does that make sense? So things get a little hit and miss there. So he might decide, and actually, you're running Linux, you probably could even do most of the things we're doing in here directly on Linux, because we're doing a lot of stuff from terminal.
Oh, you mean it's just on like Mac OS?
Yeah. But I won't do that as examples, but you probably could work, so you can decide how dangerous you want to be. But I'd encourage you to use Linux, but choose your poison. Technically, you're running Unix already with your Mac OS, because all the stuff we're going to be doing is from the terminal anyways. Or at least a lot of it. All right, so Linux uses relatively small amount of system resources. So if you're setting up a virtual machine with a common laptop setup, maybe most of you have like 8 gigs of RAM and a quad-core CPU or something, give it 1 CPU and 4 gigs of RAM, or 1 CPU and 2 gigs of RAM, and you'll probably be pretty happy. And your host operating system will still run. Where if Jack gives it too many resources, then Linux might feel pretty good, but his host operating system is like non-responsive. He can't even check his email or something like that. So that's the trade-off if you're running in a virtual machine. A virtual machine is a good way of power users to take advantage of extra hardware to run multiple things at the same time. If you don't have the extra hardware, then you can dual boot, where your machine is just running one thing at a time, have a second machine, maybe it's a Raspberry Pi, whatever it is. You do have options. All right, but for those of you who are going to do VirtualBox, in fact, I want to say that VirtualBox might even have a thing specifically for Ubuntu. I don't use VirtualBox, so I haven't actually gone through that process, but yeah, here's VirtualBox 1804, 1810, 1904. That's weird.
That's to download for Ubuntu though. Like if you download it.
Oh, for Linux host. Yeah, I see. Yeah, this is if your operating system is Linux. You're going to want VirtualBox for either Windows or for Mac. But in any case, figure it out. Get a version of Linux on one of your machines. I'll use Ubuntu in here as our example. So I'm using Ubuntu 1804. And this will get the job done. All right, so this is running it as a virtual machine. Now, if you're using Ubuntu, we're going to spend most of our time here running off of the terminal. So I just do a search for terminal here. That brings this guy up. I think I can move this. Well, I probably would have had to do it from out here. Add to favorites. That just puts it over here so I can get to it more easily next time. Well, whatever. I'm going to make the font bigger.
I think you have to go to custom font.
So can we all see that? We can read that? Okay, good. So can I now. so we're in business. All right, so something that in Linux, something that we, if you're running anything that's Ubuntu, actually, most of the modern Linux versions, and this is just not a modern thing, it's been around for a while, have package managers for installing software. Because historically, if you were a Unix user, you would have downloaded something called a tarball. So it's a .tar.gz file. Those are called tarballs. Sometimes they're a .tgz file. So that's a tape archived and then gzipped. So a zipped tape archive file. And then you would have to configure it, then compile it, and all this stuff, because you're actually compiling somebody's distributed C program for your operating system. And that's how Linux worked for a long, long time, and it still works that way today. Sometimes you'll be put into a situation where there isn't a package available. There isn't an installer available if you're thinking about it from the Windows or the Mac world, where you need to actually compile the software for your operating system. But to make life a little more convenient for Linux users and also easier to update stuff, there's a couple of well-known package managers. One of them is called apt-get. Another competitor is called Yum, L-U-M, Y-U-M. SUSE also has one, I forgot the name of it, but there's several different package managers out there. Ubuntu uses something called apt-get. So does Raspbian. Raspbian, which is actually a distribution of the Debian distribution of Linux, also has apt-get installed. So one of the things this book asks you to do initially, why is this part in here not getting bigger? No, whatever. All right, so anytime you see the word sudo, S-U-D-O, that says do this as super user. So if you've ever been on Windows and it says run as administrator, sudo says the same thing. All right, so it'll ask you to put in your super user's password, because usually you don't want to use your computer as administrator. You're using your computer as some logged in user, and sometimes you need to, if you're going to install software on the machine, you need to do that as the super user. So that's what sudo means, do as super user. Make sense? And then we're making a call to a pre-installed program here called apt-get. We're telling that program to install something. And what we're going to install is a couple of packages. So one's called, hold on, I'm not on the right thing here. It's okay. This guy does something very similar. See, almost the same starting point. Okay, so apt-get install, something called build essential. So this gives you a whole bunch of stuff like make and GCC. Well, GCC is probably already installed. So these are things that allow you to easily compile things. Then we have something called NASM, which is a assembler, because we're writing some low-level x86 Intel assembly. So NASM is an assembler. Gen ISO image. So this is something that allows you to create an ISO image, because ultimately what we're going to do is our first sample operating system, which we'll probably get to today, at least as a sample. We're ultimately going to produce a ISO, an image, and then use Box, BOCHS, to emulate a x86 or an i386 computer. Fake software or fake hardware, like pretend like we have a computer to run our operating system. All right. And then we have this thing called Box STL, and there's some other ones we can use, but this is giving us a graphical user interface to it. You can actually just do it from the terminal. So if you end up really having to go budget pleaser with yours and not be able to do a graphical thing, Box can be 100% non-GUI. Yeah, so we can make it work. But so these things here say, I'm going to give you a virtual machine. This guy's actually an emulator instead of a virtual machine. So he's emulating the 386 computer architecture. This guy knows how to generate an ISO image. This guy knows how to compile or assemble a low-level code. And this guy allows us to do some, building a, using make. You'll see that in a little bit. And apt-get is our package manager. We're telling this guy to install as super user. Make sense? So if you were to copy that and then open a terminal and paste that in there, for mine, I've already done this, so it's not gonna. It wants to know my super user password, so I'll go ahead and type that in. Could not. Do I already have? I'm going to do sudo apt-get update real quick, because something seems to be funky. So this is checking my system for software updates or whatever. But this guy would go through, and not only does it go and get those pieces of software, it gets anything it's reliant on. And that's the real job that these package managers solve for you with Linux. Is in the past, you would go and download a tarball, you would configure it, you would start compiling it, it would compile for 3 minutes, then give you an error saying, could not find X, Y, and Z. So then you go and have to download another tarball that was the X, Y, and Z program. Configure that, and sometimes that took you down a rabbit hole until it finally compiled. And then you came back to this guy, compiled it again, and it would get past that 3-minute mark and give you another error, could not find A, B, and C. Go and download it. Yada, 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 rinse, lather, repeat. You get pretty good. But you can kind of imagine that it's an operating system kind of built by programmers for programmers. Can that make sense? And so I really think Linux is a great operating system to use as a technology specialist, because it makes you really understand the hardware you're working with, because you're having to work at a pretty close level with it. And if we really talk about Linux in comparison to like maybe what some modern day technology users, through a similar lens, how many of you in here are iOS users? So got a couple iOS users. How many of you are Android users? Okay, why are you Android users? Some of you, it's going to be the stupid, I just hate Apple. Okay, when really you should just say, I hate all big companies that have lots of money. But a lot of Android users might say, I have a lot more control over my OS. I can install certain things. I can pull some stuff off that Apple locks away, right? You are able to do some stuff on Android that Google will let you do because they're a much more open sourcey type of approach where Apple will not. Fair enough? Okay, whether you should be doing it or not, you can do it if you choose. Linux would be like that on steroids. Okay, chances are, anytime you've ever seen something about a hacker hacking this or breaking into this, they probably were using Linux. is the reality. You know, that doesn't mean everything you do on Linux has to be illegal or anything like that, but it ultimately, at the trade-off of maybe complexity, gives you ultimate flexibility of doing whatever you want, including changing the operating system and then just recompiling it and running your version of Linux. No harm, no foul. Okay, I'm gonna let this guy keep kicking. This might be something slow with the internet, but I already have this stuff installed on mine, so I'm actually just going to open a new tab here and we'll start walking through this. Okay, so we're getting some tools because we're gonna have to do a couple of things to kind of get the ball rolling here. And I'm just gonna create a quick folder. All right, so you'll have to get comfortable with the Linux commands. If you're a terminal user on Mac, you're already used to ls for directory listing. This is equivalent to dir on Windows. Actually, it's funny, Ubuntu dir works. Don't do that. People will slap you. I didn't even realize it would do that. But you'll get used to other built-in commands that are part of the Linux distribution. All right. Don't immediately assume anything that's distribution-based is graphical, because most of the stuff that we're doing here, you don't even need a graphical user interface to do. It just makes life a little easier. Sometimes that makes it less convenient. But whatever. All right. So we already talked about this guy earlier. You have your BIOS, which passes it over to a bootloader. So we have a legacy bootloader and then a modern bootloader, which then launches your operating system, blah, blah, blah. You can read through this stuff. We're going to be approaching stuff very practically in here. So you can read about what a BIOS is, what a bootloader is. We've already talked about the operating system. So what they have you go through here is something called Cafe Baby. You'll notice that these are all legal hexadecimal characters. Haha, that's I had to spell something. Get it? Haha. So if you want to spell something different, you can. But so I'm going to copy this code here. I'm going to talk through it in a screen that is bigger out here. So I mentioned, now you can use a any text editor that you want. There's text editors that come with Ubuntu. If I come in here and I search for editor, here was a text editor right here. We can use that guy if you want. Cool kids though, they just do everything from the terminal. If the somewhat cool kids that like to look like they're doing stuff from the terminal but actually aren't, will use Nano. Okay, so you probably want to start with Nano. How many of you have heard of Nano before? All right, how many of you have used Nano before? Okay. Nano's a text editor. So if I say, what do they want this to be called? They want to call this loader.s. Okay, so we'll have nano loader.s. So this opens up Nano in a text editor here. Okay, so this could all be done remotely in an SSH session or something like that. We don't have to have any sort of graphical user interface. Now, you're only allowed to use Nano if you could tell me where Nano came from.
Guess I'm not using Nano.
In the very, 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 very early days of the internet, there was an email client called Pine. Okay, Pine was the name of an email client. This is all text-based. This is way before Windows. Okay, so Pine allowed you to check your email, and Pine had an internal text editor that was this guy. Now, eventually people said, oh, hi, I'm a weakling and I don't know how to be a real Linux user. So can you give me that nice friendly text editor that lives inside of Pine but to use for everything else? They said, sure. They broke it out and it was called Pico. And then later on, they decided to rename it to sound cooler and they call it Nano. And now all the tutorials have used Nano because, you know, oh, you're Linux, you're using command line tutorial stuff. Okay. No, that's just not how it works. All right. You know, so you come in here, you notice you could type some stuff out. So I'll paste this code in here. You know, code's in there. Color codes are kind of nice, like, and it does some decent stuff. Okay, but and then when you want to save it, of course, you let's see, you do a Command O that writes it. Write the file name loader S, and then I can exit. Okay, now that's nowhere near as good as me saying, so here, there's my loader S. We're just going to go ahead and remove that because, you know, we don't want that there anymore. So I'm going to say VI loader S. VI is the text editor for real. VI came before Vim, but Vim is acceptable. Yeah, in fact, if you want to use Vim, I think Vim's pre-installed. I think Vim color codes. Loader.s. Oh, see, it's not installed. I could use apt-get to install it, but we'll just use VI. So VI is the original stream editor. Well, actually, stream editor is called SED. So it's the VI is a text editor made for Linux for people who touch type. You never actually have to take your hands off the keyboard. So we're going to go ahead and open this guy up in VI. Now, VI has, you put the editor into different modes. So if I want to write something, I have to be in insert mode. So I press I, and now I'm in insert mode. Okay, now I want to go ahead and paste this stuff. So there's my code that I'm pasting. Now if I want to save it, I press escape, then I put a colon, WQ, right quit. Way easier to use. So you can decide what stupid thing you want to use. Here, just this will drive you crazy. So let's say that you are in here and you just start typing stuff. You know, I forgot to put it in insert mode, so I'm just deleting lines now randomly. Similarly, if I just start backspacing, you know, I'm in insert mode here, but yeah, you get some weird, yeah, but you have to know how to use that editor. Okay, so yeah, this is probably not for you, Luke, but you want to work your way up to it. Another popular thing is Emacs, but, you know, Nano is what most of the things will have you use as your, so whatever. So in any case, if we're looking at this, how are we doing on time? Oh, we're good. Okay. So this is a assembly language in x86 assembly, Intel assembly. All right, and we're creating this thing in something called ELF format. Okay, this is an executable. This is a executable linkable format. That's what ELF stands for, and we're going to see linking here in a few minutes. But this is following a certain kind of file format that is for Linux-based executables. Okay, so we're creating this global section called loader, whatever. We're defining a couple of global constants. These are global variables. So we have this variable called magic number. We have another one called flags. We have another one called checksum. So this magic number is this, remember earlier I mentioned something about having a very specific place in memory you might want to put something? Okay, this magic number kind of works hand in hand with grub. So I didn't know the number off the top of my head, but this is the number, all right? Then we're creating this flags thing, which is like to zero something out. And here's our checksum. So this is the magic number plus the checksum plus flag should equal 0. So this is the negative version of magic number. So this plus 0 plus its negative self should be 0. Make sense? It's just math. 5 plus 0 plus negative 5 is 0. All right, that's what it's saying there. All right, so now we have our text section. All right, so what this guy is doing is it's writing some stuff in machine code. So we're going to write out the magic number, write out the flags, write out the checksum. So that's kind of our output. Now, our actual instructions here is that this is our loader. This is what this guy actually does. So this is a label that says when your operating system, kind of flash forwarding or jumping ahead, when your operating system starts, what is it going to do? It's going to move Cafe Babe, this hexadecimal number, that's fun to say, into this hardware register, which lives on the CPU. EAX is the name of one of the hardware-based variables that lives on the CPU. Okay? Don't worry about the details of this too much right now. All right? And then we have a loop section, and what does this guy do? It says jump back to the loop section. Infinite loop. That's my operating system. My operating system puts Cafe Babe into EAX, then loops for infinity. That's it. That's it. This is a highly useful operating system. No prompts, no nothing. You get one value loaded into a hardware register, and then the thing is non-responsive. It's perfect. All right. So that is some assembly code that we wrote. Now at this point, we've kind of staged it to be operating system-esque, but it's not actually doing anything yet. All right. So I have that file. Come back in here, and we're going to go ahead and we're going to build. We're going to assemble this. So I'm going to, now remember, assembly code is a low-level language, has a one-to-one relationship with the CPU, right? Okay, that's what assembly is. You know, you think back to like the 200 class, we talk about high-level languages, power tools, one-to-many relationship with the CPU, Java, Python, all those things. That's what we like. Then you have low-level languages where every line of code you write equals one instruction on the CPU. And then you have machine language. That's the CPU. With me so far? So now we're going to use our assembler, NASM, which will turn my loader.s, which is human-readable assembly, into machine code, the executable code in ELF32 format, 32-bit executable linkable file format, which is a standard. Just trust me, it's a standard. Okay? So my file format will be ELF32. Here's my low-level code that I wrote in assembly. So I could have been .java if I wrote it in a high-level language, but I wrote it in a low-level language. And I'm going to use this program, NASM, which is assembler. ASM is assembler. To take this assembly code and turn it into machine code, zeros and ones. Make sense? Done. And now we have a file called loader.o. Now if I do cat loader.o, okay, cat catonates something to the screen, so it just dumps out the contents of it.
Oh, that's fun.
That's what binary looks like if you try to turn it into something that the terminal knows how to display. Definitely not something we wrote, right? That's our executable format. Yeah, that's actually a pretty good terminal, because older terminals, when you do that, yeah, sometimes you just you broke the character set for your terminal, and now you're just typing in boxes and stuff. So whenever that happens, you have to usually do a clear. But whatever. All right, so we've written one program in a low-level language, and all that program does is move Cafe Babe into a hardware register, EAX, on the CPU, and then we've assembled it into its equivalent machine language. So far, so good? Okay, so now we have to link this for the kernel of our awesome, highly useful operating system. So I'm going to copy this code, and I'll walk through it. And what may call that? Link LD. So nano link.ld. Gonna get a rash from using nano here. All right, so what this guy is doing is this file is going to be used by our linker, which we'll do here in a few minutes, to bring the code we just wrote, that the machine code, the already assembled code, into the correct place in memory for our operating system to actually load. All right, okay, so code should be loaded at 1 megabyte. This is grub stuff. So we talked about grub as being a bootloader. Anything below 1 megabyte in grub, the first 1 megabyte is grub specific stuff. So you got to load it at 1 megabyte. So it's like what happens after grub does its magic. All right, as it starts walking through memory. All right. So I don't even know what this does, but it does something with the text sections of all files. Notice here, if we scroll up here, remember this guy has a text section. Text, we align 4. Here's our writing out our 4 different values. So go back in here. So this aligns at 4 kilobytes. It's going to put all of our sections that are the .text sections. For us, we don't have one. We have one file that we're linking together. So we're doing a whole lot of work here when we are really, think about this in terms of, let's say you're writing Microsoft Word. You might have 50 .o files. You know, like we just created one. It probably actually be more than 50, but let's just say 50 as an example. And you want to link these guys all together into a single executable that you can run. All right, so you have to kind of collect all the parts of those together to create the linked executable. And the linked executable, the format for that is defined by the ELF library, the executable linkable format. So we're following a standard here. So we're going to bring together all the text sections. We're going to bring together all the read-only data sections. We're going to bring together all the data sections. We don't actually have a BSS section in ours, but this is what a link file looks like. The important thing for us here is just this very first part. Put it into the right place. When we link this, it needs to link into the right place in memory, the executable. All right. So I'll go ahead and I hit Control O, write it, and then Control X gets me out. All right, so now I have that file. So now I'm going to use LD. So if you ever want to know what a command does, you type man, this is the manual page, LD, and this is the GNU developer tools. This is the GNU linker. All right, so this is an open source linker tool that allows you to link multiple files together into a single executable. Number of objects in archive files, relocates their data, and ties up symbol references, usually the last step in compiling in a program. Brings it ultimately together to be an executable. Got it? All right, so I'll get out of that so you can read about it if you want to know, like, what are the things you can, what are the options I can give to LD. So it gives you some examples. You can read the whole book on it right there from the command line if you want. This is way before Google. Usually, you can make a pretty good guess. You could do a -H. A lot of times this is the help for it. So if it's not -H, it sometimes is --help. And this shows you the possible ways you can use the, this kind of gives you the Cliff Notes. Instead of it being a book thing you're reading, it just gives you the list of all the different command line arguments you can give that guy. Again, without using Google. Okay. So I'm going to go in here, and we're going to copy this. So we're going to link my link LD, that's the file we created that said put it at 1 megabyte. And we're going to do this in ELF i386 format. Going to be an i386 executable. The file we're going to link is loader.o. We would have more than one file here if we were doing a bigger application. In this case, I just have a single object file. And then so -o says output. My output will be kernel.elf. Remember earlier I mentioned that usually the names of operating systems are called kernels. The NT kernel, the 9X kernel for Windows 95, the Linux kernel. Okay, so right here we're about to doing the final step of compiling our first operating system, the Cafe Babe operating system. All right, that's why we're naming it kernel.elf, because it wouldn't be as cool if we didn't name it that. All right, so I did that, and now I have an executable file there called kernel.elf. Cool? All right, so now I have an operating system. I just need to install it and then test it. Still good on time? Yeah. Okay, so now they want you to go and get grub, because remember, we're doing this in terms of this already known bootloader. That's why we're putting it at that 1 megabyte spot. Okay, we'll talk about the details of this later. We just want to have an initial thing working here. All right, so I'm going to go ahead, and it wants us to make a directory with certain format. This follows the grub format. So we're going to have a directory called ISO with a directory inside of it called boot with a directory inside of it called grub. That's done. Then it's going to have me download this stage 2 El Torito thing. So one thing it's talking about is you can download grub, an older version of grub here, grub 9.97. So it's using a less featureful old version because our OS here is a little old school. But they've already built it for us because it works kind of funky under Ubuntu and it's a little bit hard to build. Remember earlier I was talking about building, you're compiling something. It says, oh, you're actually missing this. You got to go and get this thing. And now you're actually missing this. You got to go get something else. They've already built it for you. Say this is what you need. Okay, so you can download this guy here. I already have it. So I'm going to copy that into ISO boot grub. So I'm going to copy from downloads, what was the name of it? Stage 2. All right, so whenever you put the little tilde thing here, that says go to my home directory. So tilde/downloads /stage 2, and I'm copying that into ISO boot grub. ISO boot grub. All right, so I moved that, I copied that file there. So now the compiled version of grub is sitting inside of the grub folder, inside of the boot folder, inside of the ISO folder. And then I'm going to copy my compiled kernel, the guy I just made. I'll copy him into the boot folder. So grub says, whatever kernel is inside of the boot folder, I will load into memory location 1 megabyte. Well, that's what it wants to do. You have to make sure your linker added up to that, but it did. All right, so what I just did here is I put all the stuff in a file format that is compatible with the places that grub will look to do its job. Okay, so the trade-off is somebody already wrote grub, which knows how to load operating systems for us. And what we have to do is play by their rules and where do you put your crap for grub to do its job. Okay, make sense? So grub says put your actual kernel in the boot folder and then put the actual grub application, the executable, inside of the grub folder. And we're doing this all inside of a folder called ISO because we're going to be generating an ISO. Remember earlier we downloaded that program for Gen ISO? We're going to be building an install image for our operating system because all great operating systems are released in an ISO format, right? So technically you could take this and put it onto a virtual machine. It would be hard to look under the hood and actually see what our Cafe Babe is in EAX register because that's not nothing that's coming out on the screen. This is a real low-level, highly productive-based operating system. All right, so here's our menu listing for Grub. So I'm going to copy this. And they want us to put it in menu LST, and this is going to go inside of the Grub menu. So cd iso boot grub and nano menu.lst. And I'll paste that in there. So this is default will be our very first thing, OS. So choose by default bucket 0. Timeout is 0, which means it won't wait because you only have one OS you're loading. So we're not going to have it wait for 10 seconds before it chooses a default. It'll just choose the default. The name of our operating system is going to be called OS, and the kernel can be found in /boot/kernel.elf. That's because that's what we named our executable. Make sense? All right, so see how all these things are lining up? We had to call these things very specific things and at least make them match up. All right, so I will write this out. That should have been called menu.lst, but that's okay. I'll just rename it. So move menu to menu.lst. All right, so there's that guy. Now, this is what my file format should look like. Inside of ISO, I have a boot folder. Inside the boot folder, I have a grub folder with those couple of things in it. And also inside of boot, I'll have my kernel.elf file. Then I'm going to generate an ISO. Now I need to go back up a couple levels. So cd space ... says go up a level. / says look in the current directory. So dot is the current directory, ... is the previous directory. All right, so I'm up here. There is my gen ISO. So I'm going to generate an ISO using Grub with no emulation. Boot size is 4 kilobytes. We're going to call this guy OS. UTF-8 is 8-bit Unicode. I don't know what quiet does. It probably means there's not a whole lot of output. Instead of having 4,000 things show up on the screen as we're doing this. Boot info table. I don't know what that does, but probably puts stuff in the right place for Gen ISO. My output file will be os.iso, and my file format will be ISO. Did that. Press LS. And there is my file called os.iso. Okay. Now, we're going to need a configuration file for box. And they want us to put this in a file called boxrc.txt. So outside here, I'll do nano boxrc.txt. All right, so we're going to create a 32 megabyte machine. So remember, Box is a computer emulator. We're going to emulate a i386 computer, very old school computer. All right, we're going to use this SDL display library, which we installed earlier. My ROM image is a default. So remember earlier we talked about the things that have to happen in order for a computer to set stuff up. And the first thing that happens is a BIOS. So Box comes with a default BIOS. So BIOS box latest, and this is where it's found. User share box BIOS box beta latest, already made for us. So when we installed Box, it came with a traditional only touch this if you need to BIOS. It also came with a VGA BIOS if we wanted to actually have graphical user output stuff using SDL. So I told it where that was too. Then we're going to pretend like we have a CD-ROM. And what we're going to do is we're going to pretend like we inserted the CD that is our os.iso. And we're going to tell it to boot from that CD. We're going to tell it to put our log file inside of box log. Go ahead.
I was just wondering, do we need any sort of initial driver for like an input method? So we have one for VGA to run the graphic interface, but is there one specifically for like a keyboard?
That's what BIOS is.
Oh, the BIOS.
Yeah, this is the only one we actually need.
Okay.
If we were just running from the command line, we wouldn't even use the second part.
Okay.
Yeah, this guy gives us the ability to emulate a simple keyboard mouse based. Actually, not even. It probably does support a mouse actually, but that's what BIOS is. That's actually the magic, the special sauce of Box. Box says, look, this is a super simple 386 computer, but I give you everything that you need to test operating systems without installing it on a virtual machine or installing it on physical hardware, all that stuff. But I mean, you're probably not writing a real involved OS this way, but this gives you the basics. All right, so we're pretending like we've inserted a CD-ROM, and the contents of that will be our ISO. We want it to boot from our CD-ROM, so it's kind of like when you put the, roll back in the Windows 7 days, maybe when you put the Windows 7 DVD in and you boot it off that DVD. That's what we're doing here. All right, we want it log file to be out to this boxlog.txt, and we're telling it we want one CPU. Give us access to one fake CPU, built-in software. All right, so that's going to be my configuration file for Box here. So I'm going to go ahead and write this. Okay, and then we'll exit. All right, so now I've written my OS. I have linked it. I've built an ISO of my OS ready to launch onto a computer. I've configured my fake computer called Box. Now I'm going to go ahead and run this guy. All right, so my OS has started loading. This is that VGA output thing that it gives you. All right, now what I'm going to show you here is, now I haven't actually launched the OS yet. All right, so when you look through here, it tells you, that we've started our machine. Kind of our power button has started. All right, and if I push R right here, if I type in help, it tells you all the things you can do. And if I type in R, it shows me the current state of my registers. Okay, so right now all of my hardware registers, RAX is for 64-bit processors. All these guys are 0. So all my CPU registers currently have nothing in them. So I'm going to press C to tell this guy to continue. Kernel boot /boot kernel elf. Where do we recognize that from? Wasn't this our grub menu? So our bootloader ran here. And then what happens at the end of our operating system? After it loads into EAX, what do we see? What happens? Infinite loop? Done. Look, I did my thing. All right, so if everything worked out well here, we should be able to go and look at EAX and see that it says Cafe Babe in it. Then we know our OS did its thing. All right, so I'm going to go ahead and kill this. And I don't think I can see it here. Oh, I can. Yeah, so there's the final state of RAX has Cafe Babe loaded in it. Boom. First OS. So we just wrote our first operating system.
See, that was the whole class. You missed it, dude.
That was not worth it. All right, so make some sense? All right, so for next Monday, everybody get some form of Linux installed and get this running. I'm going to put up an assignment that has you go through and do exactly what I just did, and I want you to give me a screenshot of effectively this screen. Yep. All right, proving that you kind of have all your tools that you're going to need installed, working, blah, blah, blah. Make some sense? All right. I would recommend Ubuntu or Raspbian. If you use them, actually, I'm going to say this. Use Ubuntu if you want to follow my exact instructions here. If you're going to do this on Raspbian, message me, because what we'll want to do is we'll want to update. I can just show you what to change it to. you have a couple different options you can do with Raspbian. You can either install SDL2 on Raspbian, or you can do this as term for terminal output on Raspbian. You might actually have to install box term using apt-get install box dash term, but SDL does not work well on Raspbian. Actually, no. Out of the box on Raspbian, you can just put X there. That uses the default X windows. That'll work out of the box on Raspbian. Sound good? Okay. So we have answering no. It's just stupid. I hate Nano. Okay. Questions, comments, concerns. I'll put up once I get CSC450 extracted from 450. Because I put all the Bible homework up and stuff like that. And I said, I'll just do this once and copy it over. Mm-hmm. And then I hadn't done that for 450 because it was still 455 in my, you saw I updated because this used to be 455 and then we dumped that, it was a thing. So, but I'd already put all the assignments in for 200, so now 450 has a whole bunch of extra crap in, which doesn't take that long to delete. I just had to run the class when I did it.
So all the Bible assignments are going to be up right away then?
Yeah, I put just like last semester. So all the Bible assignments, the first one's due this Sunday, and it's staggered. It's for the first. I think it's the Bible assignments are due the first 12 weeks, but I think I push it off like around spring break and stuff like that. But you can do them all at once if you want to. My big goal with the Bible assignments is, I don't care if you knock them all out. The Bible homework isn't meant to. I also reduced how much they're worth for your grade, by the way. They used to be worth way too much. People were writing Bible. People were writing Bible homework to better grades than they should have. But it's like 10% of your grade now or something. But the real goal of the Bible homework is to get you into a habit of reading the Bible at least once a week. Once a week, I'm forcing you to read. I think we're doing Luke. We're doing the book of Luke this semester. Read 2 chapters of Luke per semester and write a little paragraph. That's the punchline, right? Same thing. I like reading it, but sometimes you guys write some pretty funny stuff. But the real goal there is to force you to read the Bible once a week. So even if you knock them all out day one, I'd encourage you to continue the process of reading 2 chapters a week of something. That's not very long, right?
No, I did for 3 days.
Yeah, for 3 days. And then you should read it for the rest of the semester. I get it. Wanting to knock them out so you don't forget about them. Because Blaine sucks at remembering to turn in.
Hey, it's a new semester, new me.
Hey, look, you're still. Any way you cut it, you're better than a Pell.
Did he not turn in a single one?
I've had a Pell turn in Bible homework 2 semesters late. I'm not exaggerating. All right. Questions, comments, concerns, bribes.
Hey, Jack, do you understand all this?
All right.